Welcome everyone. Before we run today's architectural teardown, we need to talk about why local AI development has felt so bitter lately and how the release of Gemma 4 open weights completely rewires our approach to edge pipelines. Up until now, building a localized AI agent meant stringing together multiple single purpose models. It looks impressive on paper, but in practice, it's so hectic. Every time your data hops from a transcription node to a vector database to an LLM, you incur a massive compute penalty, making true real time execution virtually impossible on the consumer hardware. But Gemma 4 fixes this by moving to a single natively multi model. Let's look at the 2 billion and the 4 billion edge variants. If you have spent time optimizing speaker diarization pipelines or building acoustic object detection systems with YOLO models, you know the latency penalty of a transcription layer. These new edge models ingest raw audio waveforms directly. It doesn't just read text, it hears the background noise, the tone, and the urgency with the near zero latency. For those of us building document understanding frameworks, you know the pain of semantic drifts. Standard RAG pipelines force you to slice your document into tiny chunks, destroying the border macro logic of the text. 31 billion dense model solves this with a quarter million tokens of window context. But you drop the entire unedited code base or a legal corpus into this prompt, and the model cross references it into a single pass. And finally, uh, the actual execute logic locally without choking your hardware. We have the 26 billion MOE, it dynamically routes data. So only 3.8 billion parameters are active at a time. But more importantly, it natively understands tool calling. It can draft a Python script, hit your local API, read the traceback error in the terminal, and rewrite the code to fix the bugs all autonomously. And this architecture represents a fundamental shift towards complete data sovereignty and zero API local execution. To see exactly how this model achieves this under the hood, let's roll the tear down.
Announced Gemma 4.
Gemma 4 is here.
Gemma under an open source Apache 2.0 license. Gemma 4 is built for the agentic era. It can handle complex logic, multi-step planning, and agentic workflows, making optimal use of tokens.
The retrieval loop is optimized. We are now running the Gemma 4 model with full context.
Modern local AI architecture operates exactly like a tightly wound mechanical watch. It looks impressive when it runs, but the sheer volume of moving parts makes the entire system incredibly brittle. Right now, developers building offline systems are forced to string together multiple single-purpose models. The result is a Rube Goldberg machine of hardware dependencies. This flowchart maps a standard acoustic pipeline. Environmental audio first runs through a transcription node, like Whisper, converting sound waves into a text string for the logic engine. But every hop incurs a compute penalty, creating a cumulative delay that makes real-time execution impossible on consumer hardware. Google recently released Gemma 4, an open weights model family distributed under an Apache 2.0 license. It targets this exact bottleneck by consolidating these distinct layers into a single inference engine. This architecture marks a shift away from micro-model chains towards single, natively multi-model models designed to handle diverse data types in one pass. To understand how this consolidation works in practice, we examine the smallest models in the family, the 2B and 4B variants. These are specifically engineered to deploy intelligence to highly constrained edge environments, like a standard smartphone or a Raspberry Pi. Their primary engineering advantage lies in their core architectural shift, native multimodality. In a traditional stack, forcing an audio feed through a transcription layer strips away critical environmental metadata. A text string cannot convey the background noise level, the speaker's tone, or the acoustic urgency of a sound. The 2B and 4B models are designed to ingest raw, fluctuating audio waveforms directly into their neural architecture. Because there is no intermediary translation step, the transcription latency drops to 0. This allows developers to build systems capable of instant speaker diarization, tracking exactly who is talking in a room in real time, running entirely on a localized microdevice. You can also train these edge nodes to listen for specific acoustic signatures, like breaking glass or a mechanical failure hum, acting as environmental triggers that function entirely offline. By processing sound natively, audio transitions from a slow, cloud-dependent data pipeline into an instantaneous logical trigger that handles real-time environmental input. But developers face a completely different friction point when attempting to parse massive, unedited text arrays or entire codebases offline. The prevailing industry assumption dictates that handling high-volume text locally requires you to build a retrieval-augmented generation, or RAG, architecture. To make RAG work within the strict memory constraints of older local models, developers have to aggressively slice unedited corpuses into tiny, disconnected fragments. This introduces semantic drift. When you map these isolated chunks into a vector database, the overarching narrative and macro logic of the surrounding paragraphs are destroyed. Consequently, when the model queries the database, it retrieves hyper-specific sentences, but frequently fails to solve the prompt because it lacks the broader systemic logic of the full codebase. Standard local RAG pipelines do not actually comprehend your documents. They fragment them, losing the exact holistic context required for complex reasoning. The Gemma 4 31B dense model was built to solve this precise semantic fragmentation. It ships with a massive 250,000 token context window that can operate entirely locally. This spec allows engineers to abandon complex chunking strategies altogether. You can load massive, unedited document arrays directly into the prompt. The dense architecture cross-references the entire corpus in a single pass, retaining the micro details securely alongside the macro context. Holding 250,000 tokens locally requires significant hardware. To run the 31B model smoothly, your machine will need at least 20 gigabytes of RAM or a dedicated GPU. In exchange, developers achieve complete data sovereignty. You can run deep analysis on proprietary legal corpuses or private codebases without transmitting a single byte to an external server. Raw context depth outperforms complex vector mapping. The 31B model allows for high-fidelity, single-pass analysis on desktop hardware. Ingestion and analysis are passive tasks. To move toward active logic execution, we have to look at the 26B mixture of experts model. A 26 billion parameter model mathematically should choke a standard developer machine, yet this model operates with incredibly low latency. This diagram illustrates the mechanics of an MOE architecture, specifically the concept of sparse activation. Out of the 26 billion available parameters, the model only activates 3.8 billion nodes at any given time during inference. It dynamically routes the data to the specific experts needed for that query, maintaining high processing speed without triggering memory bottlenecks. The true utility of this high-speed routing is native tool calling. This specific variant is not optimized to be a conversational chatbot. It is designed to act as an autonomous execution engine. Connecting local logic to local APIs used to require brittle workarounds, like forcing text models to output structured JSON using hacky regular expressions. This model supports external tools natively. You can grant the 26B model access to your local terminal. It can draft a Python script, execute the code, and if a traceback error occurs, it instantly reads the terminal output. Based on that error, it routes the logic back through a different set of experts to rewrite the code, looping continuously until the bug is fixed. All of this happens offline. The 26B MOE shifts local AI from passive text generation to active, self-correcting software engineering. Gemma 4 replaces the fragile dependencies of chained AI architectures with optimized single-pass processing. The 2B and 4B models enable zero-latency acoustic edge triggers. The 31B dense model facilitates massive single-pass document comprehension, and the 26B MOE provides high-speed autonomous terminal execution. Google released these weights under the Apache 2.0 license, granting engineers the unrestricted ability to build, modify, and commercialize these pipelines. You get the complex logic routing typically reserved for cloud-hosted environments, combined with the absolute data sovereignty of offline hardware. Let me know in the comments which model size and hardware configuration you are currently spinning up in your local environments today. In our next technical deep dive, we will tear down the 2B audio model directly, walking through the exact deployment of a zero-latency acoustic object detector on an edge device. True developer freedom is found in possessing the raw weights to execute logic entirely on your own terms, completely independent of a cloud API.